All right. Hi, everybody. I'm Dillon, as Tom said. I'm a Jansky Fellow at the NRAO. And today I'm going to be talking about detecting slow radio transients, particularly at scale. So slow radio transients are basically when new particles are accelerated by some energetic phenomenon in the universe. And these occur in lots of compact objects, not just neutron stars and black holes, but small scale objects, anything allowed by causality. So this has so far been observed in all types of stars, in stellar binaries in particular. They've been observed from various stellar explosions, supernovae, gamma ray bursts. One of them that I'll be talking about is the merger of a compact object and a massive star. All sorts of flares from supermassive black holes, regardless of whether the black hole itself shows activity in any other wavelength. And these outflows can be jetted, or they can be low velocity, very non-relativistic. There's all sorts of compact object flares, as we saw from earlier talks in this session. In one case, we saw a binary neutron star merger that produced a spectacular radio transient. And another transient I'll be talking about later is a strong candidate for an emerging pulsar wind nebula. So I put this up, and really, this is a new discovery space where slow radio transients really haven't been explored at scale before. And so there are likely more classes yet to be discovered. This is my claim. And what really gets me excited, though, beyond the discovery, is that these transients trace these short-lived but influential phases of evolution in the objects that produce them. So I'll talk a little bit about how massive stars lose huge amounts of mass for reasons that are difficult to explain by theory so far, probably due to binary mass transfer in the centuries before supernova. And this is something that you really can't probe any other way besides radio transients. Neutron stars, in the case of my one candidate, can have young pulsar wind nebulae. This must happen, right? Every object that you see in the universe was born at some point, and at some point it's a transient. And my collaborators, in particular Christina, who's over there and as a poster, have done wonderful work on supermassive black holes and all the huge diversity of flares that they can produce. And there are a lot more classes, and each class has its own questions. And once you find the transients, the questions arise. So before we can really tackle these big questions, the first thing we need to do is to solve these two basic challenges. We need to detect the transients, again, at scale, and we need to have some preliminary identification of what these transients are. If you find a radio point source that wasn't in a previous radio survey, then that's all you really have, is you have a radio source, right? But in many cases, we're able to harness all this beautiful multi-wavelength ancillary data that's becoming ever more abundant and ever higher in quality, and we're able to identify what these sources are. So if you detect transients at scale, you're able to assemble statistical samples, and you're able to do real population studies rather than chasing after single objects. And also at this scale, you're able to detect the rare objects. You're able to contrast them against the bulk population. And if you're able to identify these objects, then you can really explore the detailed physics of the shocks that arise. And you can, again, identify these new transient populations and find out what the big questions are that arise. So part one of my talk, I'm going to be talking about detection. Traditionally, the way that people have done detection is some supernova goes off, some optical transient goes off, gamma ray burst goes off, and you point your radio telescope at it, and you hope to detect it through follow-up observations. And so obviously, next generation facilities are going to have 10 times better sensitivity, and this is going to do wonders for being able to detect faint sources that you're taking follow-up observations of. And here I'm just showing the example of supernovae from this compilation by Michael Beatenholtz, where all these lines are light curves from radio supernovae that have been detected, usually by mining the archives. And the ngVLA and the SKA in 1 hour at 100 megaparsecs, where you expect 1,000 supernovae per year, are able to detect pretty much every radio supernova that we've seen so far. Whereas the VLA is an order of magnitude less sensitive. However, I want to point out that hidden at low opacity in the background are all these upper limits. And this plot is actually dominated by upper limits. And the reason why is that supernovae have an intrinsic range in luminosities, in radioluminosity, of over 6 orders of magnitude. And this is almost certainly true for other classes as well. And you can account for 2 orders of magnitude by integrating for a really long time. The difference between a 5-second observation and a 1-day observation is about 2 orders of magnitude. But it's much more time efficient to actually just go wide and fish for the ones that are actually radioluminous. It's a lottery. You don't know which ones are going to be radioluminous a priori. But if you observe a lot of sources, or if you observe a wide area, then you're able to find the ones that you actually detect. And this is radio selection. It's not better or worse than follow-up. It will probably get you more radio transients. But what I like to think of is it's just another perspective that you're bringing. You're the blind mice looking at different pieces of the elephant. Right? It's complementary to follow-up. And because it hasn't been done at scale before, we can use it to reveal new transient populations. There's lots of room for growth here. So people have been trying to do direct detection of radio transients, just comparing and contrasting radio surveys for decades. And it's been, again, a story of scale, where every time there's an improvement in instrumentation, an improvement in the size of surveys, you probe larger areas and get more sensitive. And for decades, mostly what we found were upper limits. But in the mid-2010s, there is a survey, the Caltech NRAO Stripe 82 survey, which reached a depth of something like 80 microjanskis in this 300 square degree region, SDSS Stripe 82, found of order 10 transients. And this is really promising. A bunch of papers are written about it. And it served as motivation for doing the VLA Sky Survey, which is essentially the same technique applied to the entire sky. And because they observed 100 times larger area, we're finding 100 times more transients per epoch. So we're expanding the total number of transients by several orders of magnitude. And now, once the data release comes out, the number of directly detected radio transients is going to most likely dwarf the total number of transients found through follow-up. And so I'm going to talk a little bit about the actual process of how to find these transients. To scale up to the entire sky, you really need a lot of automation. And thankfully, NRAO, their wonderful data analysts, do a lot of the hard work. They take the observations, they do the calibration, they do the imaging. And where I come in is the source extraction, where I use off-the-shelf software, PyBDSF, to find sources. And really, the secret here is doing good artifact filtering. Right? Fundamentally, what you want to do is you want to separate these 4 classes from each other. You want to know whether a region of sky is consistent with noise, whether it's a point source, and by the way, every transient, unless it's observed at a really high angular resolution and it's in the galaxy, is going to be a point source because of causality. You want to distinguish that from side lobes and stripes, and various types of artifacts. And it turns out that there's actually a pretty clean way to do this. What I've been doing lately is you know what a point source should look like based on the UV coverage of your instrument. Right? You know the synthesized beam, major, minor axis, and the position angle. And so you have a pretty strong prior on what a point source should look like. It's a 2-dimensional Gaussian in this exact configuration. And so if you force fit that Gaussian to your data at the location of a purported source, you subtract it, you get this residual. And it turns out that even in the presence of some mild calibration errors, the residuals are pretty reasonably Gaussian for real point sources. Whereas that's completely not true for side lobes and for stripes. You try to force fit something and there's still a bunch of junk left. Right? And so there's a very clean separation in this particular parameter space where the x-axis is just a p-value from a test of Gaussianity on the residuals from the histogram, and the y-axis is just the residual standard deviation. So artifacts are typically going to be much brighter than your real sources. And if you make this cut, then you find that the stuff in the top left is 99% artifacts, 1% real sources, whereas the stuff in the bottom right are 99.5% real sources, 0.5% artifacts. So you're able to do this, and all you have to do now is just see where there's noise in one previous epoch and a point source in another, and boom, you have a transient. And you repeat this over the entire sky. It's entirely automatable. You have a transient catalog. So this is what I'm doing with VLAS right now. Part 2, the really scientifically interesting part, is identification. So some sources are just in your face. They're automatically identifiable. You look at it, there's nothing in 2017, there's nothing in 2020, there's 150 sigma detection in 2023. And this is a classical nova, V1405 CAS. And there's multi-wavelength association, there's observational precedent, there's theoretical expectation. We know what this is, right? And ready for follow-up observations. But others, you want to design experiments to find. So we think for many reasons that there are lots of transients associated with galaxies in the local universe. And if you plot the normalized offset of transients, in this case, ngVLA epoch 1, not in first from the 1990s, from these galaxies, then you find there's a huge spike that at low separations that are not predicted by random points if you do the same experiment. And the population that you find looks something like this, at least the host galaxies do. And with this kind of sample, you can start doing statistics. You can, first of all, look at where the nuclear transients are, and they're primarily in red and dead galaxies, which makes sense. And the off-nuclear transients are primarily located in star-forming galaxies, right? And this automatically suggests a difference in the physical origins of where these transients come from. The red and dead galaxies, most of them are AGN, and due to the selection biases, which I can talk about later, we think they're highly non-relativistic outflows occurring at a rate of about 1 per AGN per century on average. And some of them are entirely quiescent galaxies, 3 of them, and we think that these are probably decade timescale tidal disruption events occurring at something like 1 to 30% of the optical TDE rate. Off-nuclear transients are mostly due to supernovae, we think, interacting with dense shells at about 10 to the 17 centimeters, suggestive of this eruptive binary mass tripping in the centuries before supernova, and it occurs at something up to 0.3% of the core collapse rate. Some of these are really interesting single objects on their own. Here's one that I worked on in 2021, where we had an associated X-ray flash that indicated a relativistic jet at the time of explosion. The optical spectrum and the radio spectrum tell the same story of an aspherical shell that the supernova ejected impacted of greater than a solar mass. And this was ejected several centuries before explosion, probably via binary interaction. If you plot it on this light curve plot, it's tied for the most luminous supernova ever detected in the radio. And the model that we settled on was this merger of a compact object with a massive star. I don't have time to go into details, but feel free to ask. But there's more objects that don't have X-ray flashes, but look very similar to this in both the radio and the optical. There's about 10 of them that I'll be putting out later this year. And the next thing is this flat spectrum transient that I found also in the sample of 64, where the spectral index is consistent over 4 years. It does not evolve. It's 0.35 plus or minus 0.02. And this is 7 sigma flatter than the theoretical limit from diffusive shock acceleration. You can't get flatter than 0.5 from a shock, at least from a single population. And it's fading slowly but noticeably, about 5% per year over the 4 years. And I've argued in this paper that it's too stable to be a jet, where optical depth effects can give you this kind of flat spectrum. But what it is consistent with is this emerging pulsar wind nebula, which would be a super crab, not that far away from the Crab Nebula when it was first born, just higher magnetic field, and potentially even the same spin period. And the closest observational analogs are these persistent sources associated with FRBs. So this is the scenario. You have a massive star that blows up. It's initially opaque, and eventually the ejecta become optically thin to free absorption, and you see the pulsar wind nebula within. Okay, so I have some conclusions here where we're now able to do radio transient detection at an industrial scale, and thanks to the radio selection, known transient populations are being found in statistical samples. New transient populations are being identified. But this is an ngVLA SKA conference, and so where can we go from here? ngVLA and SKA, I think, can completely change the game. So here we can apply the same techniques with slight modifications. And For example, in every ngVLA or SKA pointing, there will be Rubin LSST transients that are just happen to be in the field, and you can check whether to see you find a radio counterpart. And also, every time you repeat an observation with the same frequency, then you'll probably find transients too at the rate that we're finding them in VLAS. And so you can do this commensal transient detection, and it's very doable at industrial scale. Large samples will reveal increasing diversity and nuance in all these populations. The current techniques with SED evolution and high resolution association can be done. But what I'm really excited about is that with this jump in sensitivity, you can slice and dice your data in new ways. You can look at time, you can look at scintillation, for example. You can look at polarization, and you can look at potentially even spectral lines, either from the host galaxies or maybe from the transients themselves. And so I'll leave this up. I think that with these capabilities, we can define a new radio-defined taxonomy of transients, analogous to the ones that have been developed for supernovae and other transient classes in the optical. And I think with these next generation facilities, commensal transient detection is the place to start. Thank you.
Thanks, Dillon. That was awesome. It's so interesting. I may have missed this, but do you have any orphan afterglows, any GRB radio orphan afterglows suspected in your sample?
Not in the 200 megaparsec sample. We think they're too rare to be located in that volume, but I am searching for them out to larger volume.
Okay, great. Thank you.
Yeah.
Yeah, really cool stuff, Dillon, and that amazing that imaging of the nuclear sources and the non-nuclear sources association was really powerful. I look forward to reading that paper. I just had a quick question with the nuclear stuff, right? How do you know that's not potential scintillation, you know, just bumping it up above your threshold as opposed to, say, these flaring events? How confident you are? Maybe you know the brightness, right? They're 100 sigma events or something, but...
Yeah, so the main reason why I think it's not scintillation is because a lot of these are detected at very similar flux in epoch 3. And so you wouldn't expect it to have the same flux and be slowly evolving. Scintillation is a really short timescale phenomenon.
Yeah, cool. And can I have follow on a question? Yeah, you didn't mention any radio stars. Obviously, you must be picking up stars in this in general. Mm-hmm. How many have you found? What type of stars are they? Is that something you're investigating?
Yeah, I have a student working on this, Carlos Ayala. He's found about 80 of them. Yeah, in epoch 2 versus epoch 1.
Very interesting talk. I'm going to ask a question I asked earlier. I'm going to ask it now to you. What is the information? So we're going now this route where we're going to find lots of interesting objects. What's the other data sets that you still need? So we're going to have Rubin optical. Do you need the far infrared, for example?
Everything helps. You're, again, blind mice looking at different pieces of the elephant. Every little clue that you can put together helps. I think redshifts are particularly important for extragalactic transients. Spherex will be extremely helpful in that regard. Deep imaging, also from Rubin, and infrared imaging in particular, will look at the obscured population and the high redshift population. And that's another one, right? If you look at the depth of pan-stars, a third of these transients have no association, but if you drill deeper and redder, then you find a lot of them have faint counterparts.
Wonderful talk, wonderful work. You mentioned you're looking for point sources because of causality, and that totally makes sense at the VLA scales. But if you go to VLBI scales, then you're able to see structural evolution. So I was asking if you have any perspective on the long baselines for ngVLA and SKA VLBI to really help understand then the physics of these various classes.
Yeah, that would be absolutely beautiful to have spatial information. And we can already do it in the galaxy, as we saw in James's talk earlier, with X-ray binaries. And being able to do this at extragalactic scales would be amazing. It would, of course, require slightly new techniques. But as long as you have a model, a reasonable, flexible enough expectation for what you're looking for, then you should be able to detect, separate this from artifacts in an automated way. And I think machine learning is really the frontier for this. I actually downloaded TensorFlow on my workstation, and I'm going to try out this 5000 by hand classified thing and see whether I can do better with something like a convolutional neural net. when I get back.
Okay, so let's thank Dillon again.